neutrino, whether it's an electron neutrino, a muon neutrino, or a tau neutrino. There are three types. Neutrinos are very commonly made in a bunch of different interactions. It's almost like the neutrino is basically this side product, this particle that kind of chills, and other things will decay into it because it's a stable fundamental particle. So even if you made a pion, if it's a charged pion, you'll probably get neutrinos at the end. If it's a neutral pion, you'll get photons. And that photon can, by the way, go and excite something else, and then through that interaction, ultimately, again, you get neutrinos. So neutrinos are the side product of many, many different interactions. They're fundamental and they're stable and they're weakly interacting. So they don't go and interact much more. And so we expect that if we build good detectors for neutrinos, and we'll get into what that means, good detectors, right? Because that's going to be a whole challenge. We expect that we should be able to pick up on signatures of these neutrinos because they don't interact much. So once they're formed in these various types of reactions and interactions happening between when they were made to when they come to Earth, we expect that they would not have interacted much more along the way because they are stable and fundamental and they're weakly interacting. They only interact through the weak forces and through the W and Z bosons. They don't interact with electromagnetism. They don't interact with the strong force. They don't have much mass. They're not charged, so they're not going to get deflected by, say, magnetic fields in a galaxy or something like that. So we expect that they should come straight to us after they're made, and they should point straight back to where they came from. So it's almost like light coming from a source, but not really light. It's a neutrino, and it should point straight back to its source. So that's the whole point of the neutrinos. We expect that they will be stable and good messengers of astrophysics, but they can be incredibly difficult to measure depending on the energy of the neutrino and so on and so forth. So we'll get into the challenges part as well, but this is the whole story of why the neutrino is also considered a messenger and sort of an example of how they're made. Okay. So real quick, before I pause, I will just finish up the rest of this part. We will talk about a couple different ways in which neutrinos can be detected. So one way is optical Cherenkov neutrino detectors. So now that we've established that neutrino is a cosmic messenger and potentially they're made in these types of interactions, we just have to detect them now, right? For that, we have to build very special, specific detectors for neutrinos and deal with the challenges of neutrinos. The same things that kind of make the neutrinos difficult to detect are actually why the neutrinos would be potentially a good messenger, because if they don't interact much with most things, then they're more pure messengers. They should point straight back to their sources instead of being deflected and losing energy and things like that along the way. So there's a big reward potentially of detecting these neutrinos. That's why we work on them. So one way to detect them is the optical Cherenkov neutrino detector. Optical Cherenkov neutrino experiments look for high energy neutrinos in the energy regime of 10 to the 11 to 10 to the 15 eV. So they're not as high as ultra high energy neutrinos, but they're still pretty high energy. In this section, we briefly introduce two optical Cherenkov experiments, IceCube and Antares. Being located in complementary hemispheres of the Earth, these two experiments have complementary